In the last lecture, we designed the dynamic duo of robotic behaviors, namely go to goal and avoid obstacle. And the question I want to talk about in today's lecture is really, how do we combine these two? So let's say that I actually have, as always, a blue robot here, a goal here, and an obstacle here. With go to goal telling me to go in this direction, and avoid obstacle telling me to go in this direction, which is straight away from the obstacle. How do I actually combine these two? And the question is really this, right? Is there some blended version of the two directions we should go in, or should we actually switch between the different behaviors in a hard way so that the winner takes all? And these are really the main two options at our disposal. And what I want to do today is just discuss almost philosophically what are the pros and cons associated with these two options. And then in subsequent lectures we will be a little bit more technical in terms of how to actually build these so-called arbitration mechanisms. So mechanisms for transitioning in and out between different behaviors. So the philosophical question is really this, right? Can robots chew gum and walk at the same time? Meaning, can they do two things, or should they do two things, or should they really only be doing one thing? So the same cartoon here over on the left, where the black arrows again are the directions in which we think that the robot should go. So if we're going with the hard switches paradigm, what's going on is when we're, let's say, far away from the obstacle, then the robot should be doing nothing but going towards the goal, which I'm illustrated here with a red arrow saying that right now, that's all the robot is trying to do. And then when it gets, let's say, closer to the obstacle, it switches completely to the other direction, which is, in this case, straight away from the obstacle. And the reason one might want to do something like this is that we're actually designing the behaviors to do something really well. The obstacle avoidance behavior is designed to not drive into things. And hopefully we've designed it right so that we can actually trust that if we're only avoiding driving into things, indeed, we do not drive into things. Or if we're only trying to go to a goal, then we've designed our controller to be asymptotically stable so that we can actually trust that we end up at the goal. So the benefit with doing hard switches is then that we can actually trust these systems, that they are doing what they were designed to do from a performance guarantee point of view. Now, there is a drawback with this. So if you are a robot and you're just switching back and forth between going to the goal and avoiding an obstacle, let's say you're riding this robot, it's a really bumpy ride, or in general, you're going to get rather jerky motions out. And as we have already seen, if we're using odometry, for instance, to knowing where we are, then the odometric readings can get a little bit messed up if you start switching quickly. So there is the potential for having a really bumpy ride, and theoretically, this bumpy ride can translate into xeno behaviors where we're forced to switch very, very, very quickly, in fact, infinitely quickly in the worst possible scenario between the two behaviors. So on the one hand, we can trust that the system is doing what it's supposed to be doing, but it's doing it in a rather bumpy and unpleasant way. So that's the deal with the hard switches. So the other alternative, of course, is to blend the two behaviors. So the answer to this philosophical question here would be yes, robots can indeed chew gum and walk at the same time. They can avoid slamming into things and going towards goals. And I'm going to argue that all of us, when we're walking around, we're trying both not to walk into other people and go to the particular place we're interested in going to. So we do it all the time. Why shouldn't we let the robots do it? So the pro, or the benefit we're doing this, would be to get a smoother ride when we're not switching between behaviors rapidly. We avoid typically the xeno issue. So this would be an argument for blending. An argument against it is that we no longer can completely trust that we have guarantees that our system does what it's supposed to be doing, in the sense that now we're not only avoiding obstacles, so we're kind of avoiding obstacles, but we're kind of doing something else, and it's not clear that we can actually guarantee anymore that we're staying clear of obstacles. Or if we're going to the goal, while not only doing that, but something else, then are we indeed going to hit the landmark? So there are potential drawbacks with blending the behaviors, and one of them is that it's hard to guarantee what's actually going to happen. So let's first of all build both of these solutions, and then we're going to take some kind of stand here where we're going to prefer one over the other. So let's actually start with the switched hybrid automaton. So again, we have the robot, the goal, and the obstacle. And what we're going to do is we're going to use the behaviors that we designed last time. So we're saying in this case that we're controlling the velocity of the robot directly. So x dot is equal to u. This is in R2 because this is a planar robot. So it's a two-dimensional control signal. And let's say for the sake of simplicity that the go-to-goal behavior is simply a proportional regulator driving x to the goal. And as long as k GTG is positive, we've seen that this is an asymptotically stable controller. And we're also using the avoid obstacle controller that's just simply pushing us away from the goal. So this is actually an unstable controller that's driving us away, straight away from the obstacle point. So let's say that we have these two behaviors. Then here would be a hybrid automaton that switches between these two behaviors. So the robot is going towards the goal until the distance to the obstacle, so this distance here, dO, is less than or equal to some critical safety distance. So when we're too close to the obstacle, we switch. And then after we've switched, we are now avoiding the obstacle. And we're going to do that until we're no longer unsafe. And what I've written here is that d obstacle should be strictly greater than d safe plus some epsilon. And the reason we want this epsilon here is that we don't want to end up switching too quickly. So if we get rid of the epsilon, we're immediately in the situation where we might have Zeno or very, very rapid switches. So this would be a switched hybrid automaton that switches between behaviors, and it's kind of clear how we would design that. Blending, on the other hand, is not as straightforward. So let's say that we have the same setup as before, and let's define a blending function as a function of the distance to the obstacle. So this blending function is going to be, for a given distance dO, it's just going to take on a value between 0 and 1. And the idea is that if this is 1, say, we're only going to the goal, and if it's 0, we're only avoiding obstacles. So here's an example where sigma is 0.75, which means that I take 75% of this vector, and I take 25% of this vector. That's what the blending is doing. And what I'm doing now is I'm taking this little snippet, adding it on here, and getting this as my new direction of travel. So if I do that, I get the green arrow here. And the green arrow would now be the blended direction. So x dot is going to be 0.75 in this case of going towards the goal, and 1 minus 0.75, which is 0.25 of avoiding obstacles. So this is a very natural way in which you can actually blend these two types of behaviors. Now, you have to design the blending function, and a very standard way to do it is something like an exponential like this. So what's going on is sigma is basically 1 for large dO values, and when sigma is 1, that means that we're only going towards the goal. And then as we get closer to the goal, so d naught becomes, or dO becomes small, then all we're doing is avoiding the obstacle. And basically, the parameter here you get to tweak is beta, which tells you how quickly is this thing going to decay off. Is it going to go like this, or is it going to be slower? That's really the design choice we would have to make if we're using this kind of exponential blending function, which, for the record, is quite standard. So the punchlines behind this lecture is really that we have two choices when it comes to switching or mixing behaviors. One is to switch hard between avoiding obstacles and going to goal, and the other is to kind of blend them. And as we've seen, there are drawbacks and benefits with both of them. So if you're switching hard, you can guarantee that your system doesn't do anything stupid, but you get a bumpy ride potentially out of it. If you're blending, you get something much nicer and smoother out, but the guarantees are kind of gone. So, of course, what we want to do is have our cake and eat it, meaning we want to take what's best with both of them. So we want to get the performance guarantees that the hard switches give us, but the smooth ride that the blending gives us. And the answer to that is, surprisingly enough, going to be this induced sliding mode that we've already talked about. That is going to give us the means by which we can walk and chew gum at the same time, yet somehow guaranteeing that we don't trip over just because we started to chew gum. So in the next lecture, we're going to start approaching this issue.